This is the first classical problem from the 2024-25 fall term, Physics 105, first midterm. In this problem, we have a river. This is term 1, problem 1. And we are given the velocity of the water in this river. The velocity of the current is VR. So this is, of course, velocity of the water with respect to ground, in more familiar terms perhaps. And we have a student that swims upstream against the river current direction, a distance t, and then back to the starting point. So we have a student that swims some distance and then back. The total distance covered in one direction is d. The student can swim at speed vs. Okay. They go some vs, and this vs is the velocity of the student with respect to water. Okay. So they give us the speed of the student with respect to still water. Expression answer in terms of quantities given the problem, and some constants is needed. Now in part A, what's the time interval delta t required for the round trip? Okay. So for the time required to go upstream and then downstream. Now this time, total time, is of course going to be the time required to go upstream plus the time required to go downstream. Okay. Now this student must be swimming faster than the velocity of the water of the student with respect to water must be faster than the velocity of the water with respect to the ground, so that they can actually swim upstream. Otherwise the current will just drag them downstream. They will never move upstream. As they are going upstream, their net velocity is going to be Vs minus VR. Okay, so that's given as VR. And they are traveling a distance of dt, so t up is going to be d divided by their velocity, that's Vs minus VR. Now, when they are going downstream, regardless of what their velocity is just going to get added to the velocity of the river with respect to the ground, and their total speed with respect to ground is just going to be their velocity plus the river's velocity. So in that case, delta t down is going to be, again, they are covering the same distance, but this time with a much larger velocity, and we have to add these up. When we add these up, d is common, we multiply everything over, so d delta t is going to be dvs plus dvr plus another dvs and minus dvr. And of course this d is distance, it's not the derivative or anything like that. We're not talking about differentials here, it's just some number divided by the product of these is a minus b times a plus b is of course a square minus b square. These guys add up, these guys go away, and we end up with 2d vs by vs square minus vr square. Okay. And this is what's given in the answer sheet. Now for part B, assume that the river does not flow. What is the time interval delta t required for the round trip in still water? Well, this you can do almost in your head. We can also do it more formally, but if the velocity of the water is just 0, then the velocity of the person with respect to the water is also the velocity of the person with respect to the ground, and they cover a distance d in the ground's reference frame. They in fact cover a total distance 2d, so delta t is the part B. The delta t is just going to be 2d divided by velocity of the student. Okay. That's it. And just remember from part A, delta t was 2d vs divided by vs square minus vr square. I'm writing this down, this is for part A, because in part C they're actually asking us to make a comparison. Show that the round trip takes longer when the river flows. So this is when the river flows. They're asking us to show that this number is actually larger than this number. Now, at the first sight, they don't actually look alike, but this one is equal to 2d vs divided by vs square. So this way we make the numerators of the two numbers the same, and we can compare the denominators. Well, this is Vs squared, that's Vs squared minus something squared. Something squared is always positive, so you're making this Vs squared smaller. Remember, for us to be able to swim actually upstream, the velocity of the river, Vr, has to be less than the velocity of in the still water. So this never becomes negative, the denominator never becomes negative, but this becomes closer to zero. Okay? So consequently, this is a smaller denominator, and this is a larger denominator, so delta t part A is going to be larger than delta t part B. There are, of course, many ways to approach this. I think the easiest one is really multiplying numerator and denominator in part B by Vs. One thing you should not do is to plug numbers in and make a comparison, because that only shows that these numbers are, it's going to work for these numbers, but it's not a general proof. Okay? Saying something like, if I make the numerator smaller, it's going to, whole number, the total number is going to get larger, is something more general, okay, regardless of what numbers you plug in. But if you just plug the numbers in, then it's not as convincing a proof. It might be enough to convince you, but it's not, it would not constitute a good analytical proof.